This is a rational inequality, and we said the way that we solve these, there's 4 steps. First step is we solve it like an equation. And the way that we solve it like an equation is we just say 2x minus 1 over x squared minus 2x minus 3 is equal to 0. And then we could just cross multiply to solve this. Cross multiply just means you do 0 times the denominator here. And set that equal to 1 times 2x minus 1. You just get 0 is equal to 2x minus 1. Bring the 1 over and divide by 2. You get x is 1/2. Thank you. Okay, yeah, it'll just keep going around. So the first step is we solve it like an equation. The second step is you set the denominator equal to 0 and solve. So the denominator is x squared minus 2x minus 3. We talked a lot about factoring in this class. So the way that you factor this would be x minus 3 and x plus 1. And then you set those factors equal to 0, and you get x is 3 and x is -1. So at this point, we have 3 numbers. What we're going to do is we are going to make a number line and then figure out which region of that number line works. So for step 3, we're going to test values on a number line. So I'm going to eat into the second one a little bit. The numbers that we have on a number line are -1, 1/2, and 3. So on a number line, this area represents numbers less than -1. This is between -1 and 1/2. I have to write small to fit everything. These numbers, here, let me rewrite this. These numbers are between -1 and 1/2. These numbers are between 1/2 and 3. These numbers are bigger than 3. I think this might have been one of the sections when I was sick, and I pleaded with you to watch it on YouTube. Right? So anyway, we're going to pick numbers in each of those regions to test them. So for any number less than -1, I'm going to pick -2. For a number between -1/2 and -1 and 1/2, I'm going to pick 0. Between 1/2 and 3, I'm going to pick 1, and bigger than 3, I'm going to pick 4. Now, what we're going to do with those numbers is we're going to plug them in and see which ones work. So this is where your calculator comes in handy. I'm going to plug them into the top and into the bottom. You just have to plug them in correctly. So I'm going to go ahead and do this here. You should be doing it also to make sure that you can plug it in correctly. And I'm going to plug in -2. So if I plug in -2 on top, I get -4 minus 1 is -5. If I plug 0 in on top, I get -1. If I plug 1 in on top, I get 1. And if I plug in 4 on top, 8 minus 1 is 7.
So you can't do this if it's set equal to 0. You can only do it if it's greater than or less than.
You could do it for both. And then I'm going to plug in for the bottom numbers. If you plug in -2 to the bottom, I'm getting 5. If you plug in 0 to the bottom, I'm getting -3. If you plug in 1 to the bottom, I get -4. And if you plug in 4 to the bottom, I'm getting 5.
You put the whole equation right in the.
Yeah, you can. The only thing you have to be careful about it are parentheses. If you mess up parentheses, you'll get it wrong. But you can do it in one step, absolutely. All right. So this first one, -1 is less than 0. So I'm going to circle this because that's true. 1/3 is not less than 0. So I'm going to put an X on that. -1/4 is less than 0. So I'm going to circle that. And then 7/5 is not less than 0. So I'm going to put an X for that. Right now, we're looking at an answer of X is less than -1 and X is between 1/2 and 3. The last step that you have to do is you have to actually plug in the boundary numbers. So the fourth step would be test the boundaries. What I mean by that is, could X be -1? Or could it be 1/2? Could it be 3? And what we have to do is we have to plug those into our calculators and see. If we were to plug in -1, you'd get an error on your calculator because you're dividing by 0. So it can't be -1. So we just say X is less than -1. We're not going to include -1. If you plug in 1/2, you're going to get 0 is less than 0, which isn't true either. So I'm going to say union with 1/2 to X. And if you plug in 3, you're going to get an error as well. So as far as your final answer, it'd be numbers less than -1 in union with 1/2 to 3. This is using set notation. That would be a complete answer. All of these notes are on my website too. Right? So feel free, you can just go online and print them out. What we just did, that's from section 1.6. Right? So if you want to look at those examples, I just from 1.6. How you doing? Okay. All right. So I'm going to keep working through this. I'm going to do letter B now, unless anyone has any questions about the last one. The last one, there's quite a few steps. Okay. For letter B, it's just a radical equation. The way that we solve those is we get the hardest radical by itself, and then you square both sides. We get 3x minus 3 is equal to 4. Adding the 3 and dividing by the 3, x would be 7/3. That would be the answer for that one. All right. For letter C, we said the way that we solve polynomials, we have a few different steps. One thing that we could do is just solve it if it's basic. Most of the time we try to factor. If we can't factor it, I taught you how to complete the square. And if you don't want to do completing the square, we could use quadratic formula. We also talked about the rational root theorem and the location principle. We'll get to those a little bit later. So for this problem, if you try to factor it, we're looking for numbers that multiply to be -6 and add up to be -2. And I don't think there are any numbers where that happens. So factoring doesn't work. So we could either complete the square, which I would imagine not many of you would like that. Quadratic formula is a little more straightforward. So with quadratic formula, A would be 6, B would be -2, and C is -1. You do have to know the quadratic formula for your exam. Quadratic formula is the opposite of B, plus or minus the square root of b squared minus 4ac all over 2a. And we just have to plug in. Common mistake that people make with quadratic formula is they don't put the whole thing over 2a. If you don't do that, I have to take off points for that. So make sure the whole thing's over 2a. And now we're just going to plug in. So we're going to take the opposite of -2 plus or minus the square root of -2 squared minus 4ac all over 2a. Put the numbers in the right place. I'm going to simplify the square root. So -2 squared minus 4 times a times c is the square root of 28 over 12. We talked about a couple different ways to simplify the square root of 28. We could either make a prime factorization tree, but I know that for the square root of 28, I know that 4 goes into it 7 times. So this turns into 2 plus or minus 2 root 7 over 12. And we could actually give it one more step and divide everything by 2. So we just get 1 plus or minus root 7 over 6. No, it's a little squished, but I'll give you a chance to take it all in, look at it, ask questions. Yeah.
So on the exam, we don't need to crunch that to the calculator and give you some decimal. That's fine.
If you give me a decimal, you're going to lose points. No decimals, right? You have to simplify the radicals. I'm glad you asked. Question?
Why'd you divide it by 2?
So it's kind of like if you had a fraction that's 4 over 10. Why would you divide, could you leave it 4 over 10? You really should simplify it. You really should simplify it. The way you simplify a fraction is you take out the similar factor on the top and bottom. So in this case, we could divide everything by 2, and this would be 2/5. It's the same thing when you have radicals. We could divide everything by 2, and you get that. Does that make sense? Okay. Any other questions with this? I'm recording this, so I record all my lectures. I'm going to post it Depends how tired I am tonight, but definitely by tomorrow I'll post it. So if I'm going too fast or if you came late or whatever, you could watch this all over again. Okay. We have to go to D now. For problem D, we have a rational equation. The way we talked about solving rational equations is you multiply everything by the LCD. This was also from section 1.6. The LCD here is x minus 1. We definitely need an x minus 1. I'm going to multiply everything by x minus 1. I'll show you all the steps. Common mistake when you're multiplying by the LCD. Sometimes people forget to do like the 2, or sometimes people forget to do the last one. You have to multiply each term by the LCD. So at this point, what happens is what you multiply and what you divide by cancel. That's why we do this technique. The x, well, not this one, we're not dividing by anything. The x minus 1's here cancel. So now there's no more denominators. We'll make it equal to 0 and try to solve it. So we just wind up with 3x squared plus 2 times x minus 1 is equal to x. We can distribute the 2. Remember, we do want to have equations that are equal to 0. I'm just going to bring the x over. And now this is just a regular polynomial, which we could factor and solve it. Or you could use quadratic formula. Just to save a little bit of time here, we did spend a lot of time talking about factoring. This would factor to be 3x and x, 2 and 1, and let's see, positive and negative. So setting the factors equal to 0, we'd get x is 2/3 and x is -1, maybe. Anyone remember the last step we have to check when we're doing these kind of problems? Yeah, you have to make sure none of the denominators turn into be 0, and if you check both of these, they're fine. If x was 1, that would be a problem, but it's not. All right, I'll give you a second. I see a lot of you writing, so I'll give you a second to get caught up, and then we'll do the next one. All right. For the domain, this was in section 2.8. When we're talking about the domain, this is one of the times I asked you to watch the video. When we're talking about domain, what that means are possible x values. That's what domain means. And there's two problems with domain. One of the problems is that your denominator can't be 0. It's like what we just talked about. The second problem is inside of a radical has to be greater than or equal to 0. You can't take the square root of a negative number. So whenever we talk about domain, those are the two things we're looking out for. Is there a denominator and is there a radical? So for this first problem, obviously there's a radical, right? So what we talked about was what's inside the radical has to be greater than or equal to 0. So we're just going to say the inside of the radical is greater than or equal to 0. Solve it. X has to be greater than or equal to 4/3. When we learn to write this in interval notation, we say that 4/3 to infinity, that would be the answer. Anytime you have inequalities, you want to make sure you write it in interval notation. Now for the second problem, obviously there's a denominator. And we said that the denominator can't be 0. So we could pick any number we want except when the denominator is 0. So let's figure out what number makes the denominator 0 and say that it can't equal that number. If you bring the 6 over and divide by 2, the domain could be any x value except it can't be -3. So if we were to look at this on a number line, here's -3. You can't pick that number, but you could pick any number before it, and you could pick any number after it. The way that you write this in interval notation to show all numbers is any number from -infinity to 3, and then any number from -3 to infinity. This covers every number on the number line except -3. If you did come in a little later, at some point, please make sure you sign in. You don't have to do it right now, but before you leave, please make sure you sign in. So that's domain values. Taking a look at number 3. This was section 2.8, I believe. And this is called a piecewise graph. It's called a piecewise graph because it's actually graphed in 3 separate pieces. This is going to be one piece. When x is less than 1, then this is the y value. This is the second piece. This only works when x is between 1 and 3. And then the third piece is y is -2 for any x value greater than or equal to 3. So the way that we graph these is anytime we're using one of these symbols, we put an open circle on the graph. Anytime it's one of these, we put a closed circle on the graph. So let's go ahead and do these in pieces. The first piece was when x is less than 1. So what I'm going to do is I'm going to start with 1, and I'm going to pick x values that are less than 1. And the y value is going to be 3x plus 2. You always start with the number that's right on the border. So if I plug in 1, 3 times 1 is 3, plus 2 is 5. 3 times 0 is 0, plus 2. -3 plus 2 is -1. -6 plus 2 is -4. And then what I'm going to do is I'm going to go over to the graph, and I'm gonna put an open circle because it's a less than, just a less than sign. I'm gonna put an open circle on 1, 5. And then it goes 0, 2, -1, -1, -2, -4. That's what that first piece would look like. And that piece only works when x is less than 1. This second piece, I'm going to pick x values that are between 1 and 3. And the y value is going to be -x plus 1. And we always, like I said, you test the borders. So we're going to test 1, and we're also going to test 3. If you plug in 1, you get -1 plus 1 is 0. -2 plus 1 is -1. -3 plus 1 is -2. So 1 has an or equal to, less than or equal to. So I'm going to go to 1, 0, and put a closed circle there. I'm going to go to 2, -1. And then 3, -2, I'm going to put an open circle there. That's what that piece looks like. And then we're going to do that last one. I'm going to pick x values that are greater than 3. And the y value is just -2 for those. So we'll start at 3, 4, 5, and we're going to have a y value of -2. So 3, -2 is right here. I'm going to put a closed circle there. 4, -2, 5, -2, and that applies for all x's that go beyond that. This is section 2.6. If you didn't watch the YouTube, or if you're a little shaky on this, please rewatch section 2.6. I did plenty of examples there. All right, how are we doing with the first page? All right, anyone have any questions before we move on? We talked about circles in section 2.2, and a problem like this is pretty typical of what we talked about. If you remember, we had to complete the square 2 separate times. So let's go ahead and figure this out. The first step to complete the square was we isolate the x's. We isolate the y's. And then all the other stuff we just get out of the way. So we're grouping the x's and we're grouping the y's. Next step is we factor out the leading coefficient. So it's always just going to be a 1 for these problems. We're just going to factor out a 1 from these. And then the next step is you take half of the middle and then square it. So we're going to take -12 divided by 2, square it, and that's going to go right here. -6 squared is 36. We're going to do the same thing with the 6. We're going to take that, divide by 2, square it, and that goes right here. So let me get a little better organized here. I'm going to write 1 times x squared minus 12x plus 36. Let me give myself a little more room. And yeah, question.
Negative 12 over 2.
So you always take half of the middle. So whatever the middle number is, negative 12, you divide that by 2, and then you square it. So negative 12 divided by 2 is negative 6. Negative 6 times negative 6 is 36. But you can't just add numbers to an equation. You have to have it balanced. So this number, we added 36. You have to offset the equation by doing 36 times 1 and then subtracting it. Similarly with the 9, we do 9 times 1 and then subtract it. And at this point, it's just cleaning up. This is going to turn into just x minus 6 squared. Remember, we always talked about taking half of the middle to write our factored form, plus y plus 3 squared. And we want to have that equal to a number. So I'm going to bring over the 36 and the 9. So that's negative 45. I'm going to add 45 on both sides. And 45 minus 29 is 16. This is our equation in what we call standard form. This last number is the radius squared. So just the regular radius would be 4 if you take the square root. We're going to say the radius is 4 units. And then as far as the actual center, when we talked about writing that, we said you take the opposite of what's inside the parentheses. So it's going to be 6 comma negative 3. That's going to be our center. All right. We'll take a look at number 5. There's 3 steps to do number 5. We talked about functions in section 2.3 is where this question's from. So this is section 2.3. They always ask this on the final exam also. So it's called the difference quotient. This is a precursor to calculus. Calculus, you talk about something called the derivative, which is just like a slope. That's what this is. The second half of calculus is called integration, which is the opposite of derivative. But anyway, for this problem, you could have a function that's 2x squared minus x plus 3. F of x means the same thing as y, except f of x tells you that that's a function. So if I were to ask you what's f of 1, what this means is you plug in 1 for all the x's. Two minus 1 is 1 plus 3 is 4. So if I asked you what's f of 1, you plug in 1 for all the x's and you get 4. Unrelated to this problem, I'm just reviewing here. So for this problem, we actually have to plug in 2 different things. One piece we have to do is we have to plug in x plus h for all the x's. So the first thing I'm going to do is I'm going to plug in x plus h for all the x's. Let me write it out for you. We're going to write it out where we have f of x plus h minus f of x, all divided by h. So I'm going to color coordinate everything so it makes as much sense as it could. Did you have your hand up before? I'm sorry. Did you have your hand up before or no? I thought I saw your hand up. No, I'm
No,
seeing things?
I was-
Okay. Okay, that's okay. So let's go ahead and do this. F of x plus h means we're going to put x plus h in for all these x's. That's the first part. Now I'm going to subtract f of x. Finally, I'm going to divide everything by h. That's how we set it up. One thing I just want to point out is if you don't use parentheses here, you're going to get it wrong, right? Because then it looks like you're just subtracting 2x squared. You want to subtract the whole thing. Please remember to use parentheses on this. So now let's start simplifying. We're going to have to do a lot of distributing. Still more distributing. The x's cancel. The 3's cancel. And you just have to make sure you're careful because there's a lot of moving parts here. All I'm doing is I'm distributing, combining like terms. Looks like this 2x squared cancels with this 2x squared. And in the home stretch, we just have 4xh plus 2h squared minus h. And we're dividing everything by h. So the final answer is just 4x plus 2h minus 1. Give you a second to copy that, absorb it. If you have any questions, please let me know.
Could you go to the left for a second?
Sure,
All right,
right there,
you can go back.
here.
No, I'm saying you can go back to where you were.
Okay. Are you taking notes on your phone?
Yeah, I have a.
Wow.
Yeah.
Okay. That's cool. Yeah.
Switching it to each.
So right here, when we multiply, this is going to be x times x, x times h, x times h, and then h times h is h squared, right? But then you have to distribute this 2. So 2x squared, 2 times 2xh is 4xh plus 2h squared. Does that make sense?
Yes.
Thank you.
You're welcome. Yeah,
I don't think H
I'm sorry.
is supposed to be in the answer.
It is, yeah.
Oh,
All really good questions. I appreciate the engagement. Sometimes I make mistakes, you know. Glad that you guys are curious and you're engaged. Okay, I am going to keep going here. So in the last few classes, we talked about rational root theorem, the P over Q, and we talked about the location principle, which was the whole synthetic division between what numbers, that kind of thing. So sometimes it's hard for people to know like when to use which one. So the exam is just like this. I just changed the numbers. So I'm telling you, this is the P over Q problem, right? So what we have to do, we'll go through this like we did the ones in class. For the number of possible positive roots, we're looking for the sign changes and then we subtract 2. So it looks like a positive x to the third, a positive 3x squared, a negative 25x, and then a positive 21. Looks like it changes here, and then it changes back. So we're going to say there's 2 or 1 positive roots.
I thought it was 2 or 0.
It is. We subtract 2. Thank you. For the number of negative roots, we change the signs of the odd powers of x. So for those powers, we're going to write the opposite signs. So it's going to be negative, positive, positive, positive. It looks like there's just one change. P, if you remember, was factors of 21. The numbers that go into 21 are 1, 3, 7, and 21. Q are factors of 1. Factors of 1 are just 1. So we write 1 over 1, 3 over 1, 7 over 1, 21 over 1. And then when we go to find the roots, we're just going to do synthetic division until we get a remainder of 0. So if you start with 1, hopefully we get a remainder of 0. It's going to be 1, 3, negative 25, and 21. Remember, we add going up and down. 1 times 1 is 1, add the 3. 1 times 4 is 4, add the negative 25. 1 times negative 21 is negative 21. And it's a beautiful thing that we get a remainder of 0, which means one of the 3 roots is 1. What we're left with is called a depressed polynomial. Which is always 1 degree lower than the original problem. So if the original problem was x to the third and you already found one of those roots, this is going to start with x to the second plus 4x minus 21, which factors and we get the other 2 roots, which are 7 and negative 3. By setting those factors equal to 0. Wait. Now remember earlier in the problem, how many positive roots were we supposed to get? 2. And how many we get? 2. 1 negative, we're supposed to get 1 negative. So it all makes sense. Any questions with that page? Yeah.
We get the positive point on the X.
Yeah, I factored this wrong. Thank you. That would make more sense. We're supposed to get 2 positive and we did. All right, 1 negative. Thank you. Yeah. How we get negative where? The B? Yeah, of course. This comes from section 3.3. It's called the rational root theorem. And the way you get the number of negative roots is you change the signs of the odd powers of x. So like odd would be 3 or 1. Instead of those signs being positive and negative, you switch those to be negative and positive. Does that make sense? And then you count the sign changes from there. Any other questions here? Okay. Number 7 is like the last one we did in class. This comes from section, this is also 3.3. And I gave you plenty of room over here to do our big tables. Remember, we make one table for the positive x-intercepts. We make one table for the negative x-intercepts. Generally, we start at 0 and we go up to 4. We might have to go further. We might have to stop earlier. But this is how we always set it up. And for the positive x-intercepts, we use the leading coefficients of 1, -3, -2, and 3. For the negative x-intercepts, we're changing the signs of the odd powers of x. So -1, -3, +2, and +3. And then this is just synthetic division until you get a line of numbers that are either all positive or all negative. 0 doesn't count. If you get 0, you have to keep going. So let's do the synthetic division. Bring down the 1 times 0, -3 times 0, -2 times 0, plus the 3 is 3. So it looks like the signs keep changing, so we're going to have to keep going. Bring down the 1. 1 times 1 is 1 plus the -3. -2 times 1 is -2 plus the -2. -4 times 1 is -4 plus the 3 is -1, which looks like we have a root right here, but we haven't hit our floor yet. Bring down the 1. 1 times 2 is 2 plus the -3. -2 plus -2 is -4. -8 plus 3 is -5. Numbers are still changing. Looks like we're waiting for that -3 to go positive. Bring down the 1 times 3 is 0. This would be -2, -6. So remember, 0 doesn't count. We have negative numbers anyway. So let's keep going with the 4. That's 4, so this would be 1. 4 is 2. 8 and 3 is 11. We get another root here, and we also hit an upper bound. The upper bound is x is equal to 4. And there are roots between x equals 0 and x equals 1, and between x equals 3 and x equals 4. All right. For the negative roots, we're going to do the same process with different numbers. Bring down the negative 1. This would be negative 1, so this is negative 4, negative 2, and 1. Bring down the negative 1 here, times 2 is negative 2, so this is negative 5. Negative 10, so this would be negative 8. Negative 16, and 3 is negative 13. So it looks like we hit a lower bound. The lower bound, why wouldn't it be 2? It has to be negative, very good. And we also know that there's a root between x equals negative 1 and x equals negative 2. Yes.
How do you get like the numbers for the negative one? Like, it's cheap. That's not. Like,
All right, so let's figure this out. Which one are you pointing?
the negative one. I know you got the 1, the negative 3, negative 2, and the 3 from the original equation. But I thought you just changed the signs around.
Well, you do change some of the signs. You change the signs for the odd power steps.
Oh,
So see how that's x to the third?
yeah.
It's positive x to the third, plus these are negative.
Okay, so for the odd.
Yeah, and same thing with the negative 2 to the x to the third. One is on, so we make that positive.
Oh, okay.
You're welcome. Anyone else have questions? All right, for a problem like number 8, this was in section 2.6 and 2.7. In section 2.6 and 2.7, we talk about graphing. This is a really important section. I'll give you a little summary of 2.6 and 2.7. We have what are called parent graphs. Parent graphs just tell you what the shape of the graph looks like. So if you have y is equal to x squared, the graph is going to look like a parabola. If you have a square root, the graph's going to look like a hook. X to the third, the graph looks like this. And a cubed root, the graph's going to look like this. Those are what are called parent graphs. This graph, it's x to the third, so we know the graph's going to look like that. We even talked about that in our last section. I gave you a table and I showed you what the graphs look like based on their power and if they're even or odd. So we know the graph's going to look like that. In addition to the parent graphs, we have something called transformations. Let's take a parabola, for example. So transformations, looks like this. Obviously, it's a parabola, but all of these different numbers do different things. So this 3 on the outside, this moves the graph either up or down, depending on if it's positive or negative. So this particular graph says -3, so it's going to be moving down 3. The +1 on the inside, this moves the graph either left or right, depending on if it's positive or negative. This is +1, so this graph's going to go to the left. And then we have the outside numbers. This negative is just going to reflect the graph. So instead of the graph looking like this, the graph's going to be upside down. The other thing that's going on here is this 1/2. If that number is bigger than 1, we call the graph a vertical stretch. And this just makes the graph narrow. If that number is less than 1, this is called a vertical shrink. And it makes the graph wide.
Well, I get points off, I call this equation instead.
So those are the major changes for transformations. I'll give you a second to copy that down, and then we'll go through this graph. Okay. So that's huge. The number one most important thing in math is factoring. That's the most important topic in math. The second most important topic in math is graphing transformations. We just covered about a week's worth of high school algebra in 2 minutes. So let me show you how that comes into play with this problem. For this problem, x to the third looks like this. So we know the graph looks like that, but there's a few changes that happen. The first change that happens is this +3. Look at the notes that I just gave you. What happens if it's +3 on the inside?
Goes to the left.
So this graph's going to go to the left 3. The next thing that happens is this negative in front. What does the negative do? Flip it, right? So we'll just call it a reflection. And the last thing it does is this -2. What does that do to the graph?
Down.
Down 2. So we're going to take this graph. Normally it looks like this. You don't have to graph it yet. First step it does is it goes to the left 3. So that's left 3. Then it gets reflected. Well, we said what reflecting means. That makes it look like this. Then we're going to move the graph down 2. So bringing this all together, that's what the graph looks like. Now, remember in our last class, we talked about end behavior. And when we talked about end behavior, I told you it was going to be multiple choice. Every option is going to have a right side. So the right side of a graph is when x goes to infinity. The left side of a graph is when x goes to -infinity. And every option has that. Obviously, all of them have that, right? What we have to figure out is the graph going up, meaning y goes to infinity, or is the graph going down, meaning y goes to -infinity? So let's figure this out. Question?
If the equation is set to f of equal to f of x or y, does that mean there's always just 1, 0?
No, so the question is, does it make an impact on the answer if it's y or f of x? And the answer is no. Y and f of x are the same thing.
Yeah.
What tells you how many x-intercepts there are is whatever the highest power of x is. So technically, this is x to the third. I mean, the graph could look like this. 1, 2, 3.
Yeah, okay, that's what I was asking, because I was thinking there should be 3, but didn't work.
That's the maximum there could be. Okay. Remember how we talked about multiplicities?
Yeah,
So you could even have a graph like this. Where, I don't know, the multiplicity is 2, 3 times, you know what I mean?
yeah.
So it doesn't have to look like the Loch Ness Monster like that, but it, it could. So anyway, let's talk about this graph. On the right side of the graph's going down. So right side of the graph's going down. On the left side of the graph, it's going up. What option is that? Yeah, this one looks like that. 3 looks like this. This option looks like this. And this option looks like that. So it looks like that would be the one that we're looking for. Remember, the My Math Lab assignments are due Wednesday at midnight. Really, you should have that done before you take the test. That's all your practice for the test. Obviously with the exam. All right, does anyone have any questions with this page? We have a couple more things to do. So on our last page, we have a quadratic equation. This is going back to section 2.6. That's where this is from. So I'll show you the easiest way to do this problem. The vertex, so first of all, this is x to the second, which means the graph looks like this. This point is called the vertex. And the question's asking us to find the vertex. The easiest way to get the vertex is to follow this formula. The opposite of b over 2a, and then we're going to plug it in to get the y value. And I'll explain exactly what this means. A is 4, b is -16, c is 7. So let's figure this out. First step, we're going to take the opposite of b divided by 2a. (16 over 8 is 2. That's the x value of the vertex.
Is that the plugin because that's like perfectly in between where the plus or minus would be? Like
That's right.
the root?
The question is the plug-in, because the quadratic formula is the opposite of b plus or minus the square root, right? So we're only taking the first part of the quadratic formula, which is right in the middle before the plus and the minus square root. So that's exactly what we just said. So we know the x value of the vertex is 2. The way you get the y value of a point is you plug it into the equation. So all you have to do to get the y value is you just plug in 2 for all the x's. And let's see what that is. I'm getting -9. So the vertex is going to be 2, -9. I'm going to go to my graph. It looks like it's a little bit off of this one, but let's put 2, -9 right here. That's how we find what's called the vertex. The way you get the y-intercept is you make all the x's equal to 0. So this is a pretty easy thing to do. Put 0 in for all the x's. Remember, y and f of x are the same thing. So we just get 4 times 0 squared minus 16 times 0 plus 7, or y is equal to 7. That's how you find the y-intercept. And then we have to get the x-intercepts. Probably the easiest way to get the x-intercepts is when y is equal to 0, we could just use the quadratic formula. And we'll just plug in our numbers, we'll simplify it, and we'll see what it comes out to. We're going to do the opposite of -16 plus or minus the square root of -16 squared minus 4 times a times c, all divided by 2a. I'm going to type that into my calculator, and it is the square root of 144. Square root of 144 is 12. And if you do 16 plus 12 divided by 8, I'm getting 3.5. If you do 16 minus 12 divided by 8, it's negative 0.5. Or I'm sorry, it's positive 0.5. So 3.5, I'll put a point. 0.5, I'm going to put a point. And then remember, this was a parabola. So we're just going to draw a really narrow parabola like that. And while you're catching up, we already talked about end behavior. This first end behavior looks like this. The second one looks like this. This one looks like this. And this one looks like this. Clearly, this graph is the first type of end behavior. Give you a second to copy it down, and then we'll do our last problem. All right. And our last problem on the exam. Even and odd. This comes from section 2.7. So in section 2.7, we talk about what it means for a function to be even or odd. And I'll give you the notes off on the side here. Even means that there's symmetry to the y-axis, meaning when you go to graph it, it's the same exact thing on the left and out on the right. Kind of like if you were to draw a line right down your body, through your nose, through your belly button, theoretically equal halves. Odd means that there's symmetry to what's called the origin. The origin is the point 0, 0. And whenever you have a graph that's symmetric to the origin, It's gonna look kind of like this. And there's a test to figure out if it's even, odd, or neither, and it's really an easy test. If a graph is even, if you were to plug in negative x for all the x's, you get the same exact equation back. So for example, if this is the graph f of x is equal to x squared plus 1, plug in negative x for all the x's, negative x squared plus 1 is just x squared plus 1. Obviously, these are exactly the same thing, which is why this graph is even. That's the test to figure out if it's even. If it's odd, what's going to happen is if you plug in the opposite of x, you get the opposite of the entire equation. So let's say we had a problem where, say this graph is f of x is equal to x to the third minus 2x. If we were to plug in the opposite of x, we get negative x to the third minus 2 times negative x, which is negative x to the third plus 2x. You see how that's exactly the opposite of what we started with? That means that it's odd. So let's go through these 3 problems. We'll run the tests and we'll figure out what they are. For this first example, if we were to plug in the opposite of x for all these x's, negative x to the fourth minus 2, negative x to the second, we wind up getting just x to the fourth minus 2x squared, which is exactly the same thing we started with. We're just going to keep plugging in negative x and see if we get the same thing or the opposite or neither. So we'll do it with the second problem too. Let's plug in negative x. We get 2 times negative x plus 1 is the square root of negative 2x plus 1. Obviously, it's not the same thing. Is it the opposite? No, it just looks different. So we say that it's neither. Now we have one more to go. For this last one, we're going to plug in negative x. So negative x to the third minus 2 times negative x gives us negative x to the third plus 2x. Doesn't look like the same thing. Is it the opposite? Looks like every term is the opposite sign. So we would say this is odd.